Welcome to Blueprint to Reality. Today, we're unraveling one of the most fundamental questions in civil engineering. Why do buildings stand? Let's dive into the science of structural stability. The concept of structural stability. At its core, the stability of a building is about balance, balancing the forces acting on it, and ensuring the structure can carry its own weight and any external loads. Buildings stand because they are designed to handle a range of forces, like gravity, wind, and even earthquakes. A stable structure means that all these forces are properly managed and redirected into the foundation, allowing the building to remain upright and functional over time. 1. Gravity and dead load. First and foremost, buildings must support their own weight, also known as the dead load. This includes the weight of walls, floors, roofs, and every other permanent part of the structure. The force of gravity pulls everything toward the earth, so the building must be designed to resist this downward force and ensure that it's evenly distributed. The materials used in construction, steel, concrete, wood, are selected based on their strength to support this dead load. Engineers calculate how much weight these materials can safely hold without buckling or collapsing, ensuring the building's foundation and frame are up to the task. 2. Live load. But buildings don't just have to support their own weight. They also need to handle live loads, which include things that change over time, like people, furniture, and equipment. Engineers account for these dynamic forces, ensuring that the building remains stable even when it's filled with occupants or heavy machinery. In areas like offices, schools, and homes, live loads can vary significantly. The design must be flexible enough to accommodate fluctuations, like a crowded event or heavy snow on the roof, without compromising stability. 3. Wind and lateral forces. Next, we have lateral forces, especially from wind. Wind doesn't just blow against the side of a building, it can push and pull on the structure, causing it to sway. Engineers account for wind loads by designing buildings with lateral support systems like braces, shear walls, or moment frames. These elements help the building resist side-to-side forces and prevent excessive swaying. Tall buildings, in particular, are prone to wind forces. Skyscrapers often use a tapered design or add dampers, which absorb and dissipate wind energy, preventing the building from becoming unstable during strong winds. 4. Seismic forces. In earthquake-prone areas, structural stability is even more critical. Seismic loads introduce horizontal and vertical forces, shaking the building's foundation. Engineers use techniques like base isolation, cross-bracing, and shock absorbers to prevent excessive movement and ensure the building can withstand these intense forces. Buildings in earthquake zones are designed to be flexible enough to absorb seismic energy without collapsing. This flexibility allows them to sway safely instead of rigidly snapping under the pressure of an earthquake. 5. Foundations and load transfer. All the forces acting on a building, gravity, live loads, wind, and seismic forces, must be transferred safely into the ground. This is where the foundation plays a crucial role. Foundations are designed to evenly distribute the load across a large area, preventing the structure from sinking or tilting. Deep foundations, like piles driven into the ground, are used for tall or heavy buildings to reach stable soil layers. Shallow foundations, like slabs or footings, work for smaller structures where the soil can support the load at surface level. Conclusion. So, why do buildings stand? It all comes down to managing forces and ensuring stability. Engineers balance the downward pull of gravity with the push of lateral forces like wind and earthquakes, transferring these loads safely into the foundation. With careful design and material selection, buildings stand tall and strong, even in the face of the elements. Thank you for tuning into Blueprint to Reality. If you enjoyed this deep dive into structural stability, be sure to like, comment, and subscribe for more civil engineering insights. Until next time, keep building the future. Welcome to Blueprint to Reality. Today, we're diving into a critical issue in skyscraper engineering. What happens when you build the world's tallest building and forget this one crucial detail? It's not just about reaching new heights. It's about ensuring that every aspect of the design and construction is flawless. Let's find out what could go wrong. The challenge of building tall. Building the world's tallest building is no small feat. Engineers and architects face numerous challenges, from structural integrity to wind resistance, and even the foundation. Every detail must be meticulously planned and executed. But what if something critical is overlooked? One crucial aspect that is often discussed, but sometimes underestimated, is the building's foundation. A skyscraper's foundation is not just about supporting the structure's weight, but also ensuring stability against lateral forces, like wind and seismic activity. If the foundation isn't designed and constructed properly, even the tallest building can face severe problems. The importance of foundation. The foundation of a skyscraper is its backbone. It must handle the immense weight of the building, which can be hundreds of thousands of tons. If the foundation is not deep enough, strong enough, or appropriately anchored, the entire structure is at risk. For example, if a foundation is not deep enough to reach bedrock or a stable layer of soil, the building may experience settlement or tilt. Over time, this settlement can cause cracks in the structure and potentially lead to catastrophic failure. Moreover, foundations must account for lateral forces caused by wind and seismic activity. Without adequate design for these forces, the building might sway excessively or even collapse under extreme conditions. Real-world examples and consequences. There have been instances where foundation issues led to major problems. A notable example is the Leaning Tower of Pisa. While not a skyscraper, it illustrates the dangers of an inadequate foundation. The tower began leaning because its foundation was too shallow and the soil beneath was unstable. For modern skyscrapers, inadequate foundations can lead to similar issues, but on a much larger and more dangerous scale. The Burj Khalifa in Dubai, the world's tallest building, had its foundation meticulously designed and constructed to avoid these issues. However, if a project of that scale had overlooked such a detail, it could have resulted in massive structural failures. The role of engineering and precaution. The key takeaway is that every detail in skyscraper construction matters, but the foundation is particularly critical. Engineers and architects must ensure that the foundation can support the building's weight, withstand lateral forces, and adapt to the ground conditions. Any oversight in this area can have severe consequences. Modern technology and engineering practices help mitigate these risks, but the principles remain the same. Thorough planning, accurate modeling, and rigorous testing are essential to avoid disaster. So, there you have it. Forgetting the foundation could spell disaster for the world's tallest building. Thanks for watching. If you found this insight valuable, don't forget to like, share, and subscribe to Blueprint to Reality for more engineering explorations. See you in the next video. Buildings, bridges, or towers, using the right software can make your life a lot easier. So, let's count down the top 5 software for structural engineers that you should have in your toolkit. Number 5. ETABS. Coming in at number 5 is ETABS, one of the most popular tools for structural analysis and design, especially for buildings. ETABS is fantastic for multi-story buildings and has built-in features to handle everything from simple structures to complex high-rises. It offers advanced analysis capabilities like dynamic analysis and seismic load simulation, making it ideal for earthquake-prone regions. If you're working on commercial or residential buildings, ETABS is a great go-to for accurate and efficient structural modeling. Number 4. SDAD.Pro. Next up, at number 4, is SDAD.Pro. This software is widely used for analyzing and designing all types of structures. Whether it's buildings, bridges, or industrial structures, SDAD.Pro has the versatility to handle complex load combinations and perform advanced finite element analysis. It supports multiple international codes, so whether you're working on projects in the US, Europe, or Asia, SDAD.Pro can adapt to local standards. It's perfect for engineers working on global projects or structures that need detailed load simulations. Number 3. SAP 2000. At number 3, we have SAP 2000, another powerful software for structural analysis and design. SAP 2000 is known for its user-friendly interface and the ability to handle a wide variety of structures, from small residential buildings to large bridges and towers. It excels in 3D structural modeling and is widely used in projects that require seismic and dynamic analysis, such as tall buildings and complex infrastructure projects. With integrated design tools, SAP 2000 is great for optimizing your structural design while ensuring it meets safety standards. Number 2. Tekla Structural Designer. At number 2 is Tekla Structural Designer, an excellent choice for those who want seamless integration between analysis and design. Tekla stands out because it allows you to design both steel and concrete structures within the same platform, saving time and improving collaboration. One of its strongest features is its ability to automate repetitive tasks, making it perfect for large projects where efficiency is key. Plus, it integrates well with Building Information Modeling, BIM, so you can easily coordinate with architects and other professionals. Number 1. AutoCAD Civil 3D. And finally, at number 1, we have AutoCAD Civil 3D, a must-have for any structural engineer working on infrastructure projects. Civil 3D excels in designing roads, highways, and drainage systems, but it's also used for structural design and detailing. It's highly customizable and integrates well with other Autodesk products, making it a versatile tool for both design and documentation. Whether you're designing a new highway or a complex steel structure, AutoCAD Civil 3D is a trusted industry standard. So, there you have it, the top 5 software for structural engineers. From tabs for buildings to Civil 3D for infrastructure, these tools are essential for modern-day engineering. Thanks for watching Blueprint TO Reality. Don't forget to like, subscribe, and hit the notification bell for more insights and tips from the world of engineering.